So now let's look at 5.3, covalent bonding. And what stands as a mystery for lots of people is why do some chemicals form ionic bonds whilst others form covalent bonds? And before we get into the details of what a covalent bond is, it's to do with the electronegativity. It's basically a measure of how strongly an atom pulls on a shared electron in a bond. Now, a covalent bond forms when the difference in electronegativity between the two atoms is very small, whereas an ionic bond would form when it is very large. So, for example, H2, hydrogen gas, both of the hydrogen atoms have the same electronegativity, so they're quite happy to share electrons. They would form a covalent bond. Sodium chloride, an ionic bond, well, sodium has a much lower electronegativity than chlorine. So sodium donates an electron to chlorine and chlorine receives it. Now, this means that in any substance where you have a diatomic or triatomic substance where an element is bonded to itself, it will be a covalent bond. But also in things like a non-metal bonding to another non-metal, like, well, H2O or something like that. Compounds that form, like carbon dioxide is another one, or sulfur dioxide, in fact. We also get covalent bonds forming in certain ions, NH4+, normally it's NH3, and what happens is you get a covalent bond forming with an additional hydrogen nuclei and it creates NH4+. And these can form small molecules such as O2, CO2, and also some giant covalent structures like diamond, and we'll hear more about that later. So how does this fit in terms of the orbitals? Well, in a covalent bond, the two outer orbitals overlap, and this means the electrons in those orbitals are now existing in both orbitals of both atoms. They're shared in between the two, and the electrostatic attraction to that electron holds the two nuclei in position relative to each other. Now, that is different in the ionic compound. In an ionic compound, there is an ion, and it is attractive in every direction. The range of the force is slightly larger, but in a covalent compound, it is very much localized between the two atoms, nestled in between there, and not detected outside. And that's why a bond will form to a nearby atom, forming something that is very, very hard to break, like O2. But not necessarily to other nearby atoms. It requires it to be frozen before you get to that point. So in covalent bonding, electrons are shared, and remember in ionic bonding, they are transferred. A dot and cross diagram is perhaps the easiest way to see what's going on. Here we've got the chemical ammonia. Now on the far left, that's the dot and cross diagram, then there's a nice picture, and then a displayed formula. Now, in the dot and cross diagram, it's important to remember that nitrogen has only got a valence of 3. It's got only 3 holes, you could say, in its outermost shell, which means it will form a covalent bond with 3 hydrogens. Now, it also leaves nitrogen with a pair of electrons that with no valence, and we would call that a lone pair because they're not involved in bonding, but ultimately they affect the shape of the molecule. Here, the lone pair at the top of ammonia pushes all of the hydrogens kind of away from it, forming a tetrahedral shape. With water, the lone pairs form almost in a linear pattern, not quite, but almost. That diagram there, it tends to be that the lone pairs both appear on the same side, making it more boomerang shaped. Hydrogen fluoride basically has got lots of lone pairs. It's got 3 sets of lone pairs, and that determines that it's going to basically be, well, in any diatomic chemical, it's always going to be a straight line between the two, but the straight line is obviously going to be away from the existing lone pairs. So I used this word valency. What exactly do I mean by that? It's how many electrons you would need to lose, gain, or share to form a complete outer shell, a stable electron configuration. And this can be found from the periodic table. Hydrogen has a valency of 1. It can share an electron. It could also take an electron in the form of a covalent bond with perhaps another hydrogen to form H2. Oxygen in group 6 has a valency of 2, which means it just needs 2 more electrons to fill to complete its octet or to fill its outer shell. That means it can form 2 bonds to things. Sometimes they could be double bonds, but more about those later. Nitrogen has a valency of 3, as we just saw with the ammonia, and carbon has a valency of 4, which is obvious when you think about chemicals like methane, CH4. This valency is linked to the number of covalent bonds that this chemical can form. They won't always gain a full outer shell. Some covalent bonds form to just share all of the existing shareable electrons. For example, boron has got 3 electrons in its outermost shell, and it has a valency of 5. But that doesn't mean it will form 5 bonds, it will only form 3. Because fluorine, in this case, can come and bond with those 3 electrons. But there's no more to share once those 3 are used up. So here it will form a maximum of 3, boron trifluoride. So it doesn't always happen that the valency matches the number of bonds it will form. It will only do that from group 4 onwards. Everything less than half an octet is not going to magically become full because it just hasn't got enough electrons to share for that to happen. So let's take a look at group 4. So carbon, for example, will form 4 bonds, and that's because it has 4 outer shell electrons and it has a valency of 4. It will accept 4 electrons in its outer shell. This is obvious with things like methane, but it can also put other things in there as well, like carbon tetrachloride has chloride or chlorine atoms in the place of the hydrogens, and it also leads to this long chain chemistry where we have, for example, at the end of a chain, 3 hydrogens and then 1 link to another carbon. All group 4 chemicals will follow this basic pattern. It's possible to create almost identical chemicals with silicon. For example, ethane, that one on the right hand side, you could make a silicon version of that and it would be called disilane. Nitrogen has a valency of 3 because it has 5 electrons in its outermost shell. That means nitrogen often forms this tetrahedral shape with 3 atoms connected to it, like in the form of ammonia or in the form of phosphorus fluoride. However, there is an exception to the rule. It is possible for nitrogen to form 5 bonds. And this breaks our understanding of how these bonds can form and their relationship to valency. It used to be considered that the reason why we can gain an extra 2 atoms joined on is that electrons were moving into the vacant n equals 3 d orbitals. Basically, they didn't exist, but electrons can go and occupy and form a wave function in the d orbital position. We now don't believe this is entirely true. We think that maybe the reason this happens is because of the formation of a delocalized molecular orbital, like a sigma bond or some such thing. The bottom line is, these breaking of the rules occur sometimes, and in reality, we don't fully understand why it's happening. If we move along the period 1 and end up in group 6, the group that starts with oxygen, we find that all of the molecules formed in here are very similar to each other, in this forming 2 bonds because of the valency of 2. Water around the oxygen is a very, very good example of this, but going down the group, you can also have very similar chemicals like hydrogen sulfide, similar in its shape, but probably not its properties. So 2 bonds for group 6, but again, we get this hybridization of other orbitals. So you can form this as an interesting sulfur tetrafluoride by, as we used to think, the d orbitals getting involved, but as we now think, the delocalized molecular bonds forming, we get a situation that looks like this. 2 extra bonds have been formed, or alternatively, we can actually have all of sulfur's 6 electrons shared in a covalent bond with fluoride, forming sulfur hexafluoride. So again, these are the exceptions to the rule. Going back to oxygen, if it can form two bonds, what if it forms two bonds with the same atom that it's next to? For example, one oxygen forming two bonds with another oxygen. It can do this. In fact, it does do this, and this is what we would call a double bond here. O2 has one such double covalent bond between them. Each oxygen shares two of its outer shell electrons, so that there is 4 shared between the two oxygens, making it a very strong bond. They have each 2 sets of lone pairs, and this forms that familiar O2 shape. Carbon, with its requirements of forming 4 bonds, can form a double bond times 2. It can form one double bond to one oxygen and one double bond to another oxygen, which would make carbon dioxide. Each oxygen is sharing 2, the carbon is sharing 2 on one side and 2 on the other side. Sulfur dioxide here also forms, and you can see that it has got a double bond between the sulfur and the oxygen, but why is it such a funny shape? It's because, unlike the carbon, it has an additional lone pair. You see, sulfur is it's in two groups down the periodic table, so it's got 2 more electrons than carbon has. The presence of those electrons pushes the double bonds away, so they're not linear anymore. They're now in a kind of like, if you imagine it's almost a triangle shape with the lone pair at the top and the 2 double bonds, the bottom left corner and the bottom right corner. Now we're going to talk more about how the type of bond and the number of bonds and the number of lone pairs affect the shape of a molecule, but that's a conversation to have in chapter 6. And now this picture top right, that's sulfur dioxide. You see it naturally forming around volcanoes. If you ever visit an active volcano, it stinks of eggs, which is of course sulfur dioxide, and the sulfur in oxygen burns with this sort of purple colour. Very cool. Now there are other double bonds, and in fact there are other double bonds in organic chemistry. For example, carbon could form 2 single covalent bonds with hydrogen, but form a double bond to another carbon. That's the kind of chemistry to do with alkenes, or unsaturated carbon chains. Now, there is a difference in the properties between single bonds and double bonds. For a start, single bonds involve just 1 shared electron, whereas the double bond involves 2. The single bond generally tends to be weaker, with a double bond stronger, so therefore it requires more energy to break those double bonds. Also, the presence of the double bond, it's stronger, and so it pulls those atoms closer together. The attraction to more electrons between the two shortens the distance, makes it a shorter bond. If you've ever made a molymod model of atoms, you'll notice that the double bonds definitely are smaller and shorter, at least it should be. So it means that the bond itself is less reactive in the saturation in the single bonds, but more reactive because, of course, you could snap that double bond and attach other things to it, things that are more reactive than carbon. And so, therefore, you can do quite a lot of chemistry if you've got double bonds existing. You can rotate a single bond. It's basically like anything. It's got a single axis, so it's easy just to rotate. However, with things that form a double bond, as we shall see later, you can't really rotate them. There's a restriction of their rotation in the same way that it's very difficult to rotate anything that is joined in 2 places because you'll start winding it up. Whereas with a single bond, there's no such restriction. So if we can have double bonds, why not triple bonds? Well, in fact, yes, we can. All you need is a valency of 3. So nitrogen has basically got, it's in group 1, 2, 3, 4, 5. So it has 1 lone pair, and then the other 3 get involved in bonding. They share 3 each, so that there's 6 in the share zone. And that makes nitrogen N2 very, very secure and well held together molecule. But we do see the appearance of triple bonds elsewhere as well. Hydrogen cyanide. Hydrogen cyanide, of course, is the deadly poison, and it gains its name from the fact that all of the cyanides, the carbon-nitrogen chemicals, the first ones that were discovered and identified, were always blue, quite often used as pigments, cyan, for example. Hydrogen cyanide, great fun. Carbon monoxide is a triple bond form, and you can see there it is. It's slightly different in that more things are being shared. Look how it is slightly crazy there. We've got, yeah, I don't like that. If you look at that diagram, I think there's a mistake in it because there's an extra X. That's one more X than, hang on, 1, 2, 3, 4, 5, 6. No, no, that's right. So oxygen has ended up sticking an additional one of its electrons into the share zone. It's quite complicated, carbon monoxide. Best to think of nitrogen as the best example of the triple bond. Now, with all these covalent bonds so far, we've imagined that both players in this chemistry have come with an electron each to share and greeting each other on mutual terms. But that doesn't have to be the case. You see, if we have something like this as sulfur dioxide, the sulfur has got this lone pair, and this lone pair sits there at the top of the molecule. But what if oxygen came along, and the oxygen needed 2 more electrons? It had a valency of 2. If oxygen came wandering along, what it could do is it could bond. It could attach itself to the lone pair. It is entirely sharing the electrons that have come from the sulfur. And so this is called dative covalent bonding, and it creates things like here, sulfur trioxide, a nice triangular shape molecule. Now, this also occurs with some ions. So if we have ammonia, NH3, that lone pair at the top, is very attractive to a H+ ion. H+ ion comes along and can attach itself to that lone pair. Why? Because it's attracted to the electrostatic charge. The H+ is attracted to the isolated pair of electrons. And so we get this, NH4+, which is ammonium, which is a very common ion. And though we will talk about this in chapter 9, here's just one little link to the future. Eventually, we're going to have to talk about the relative bond strength, how much energy is required to break these bonds. And we can see that down this list of covalent bonds here, that they're getting stronger. The average bond enthalpy, the amount of kilojoules per mole required to break all of these bonds, it is getting larger. It means the bond strength is getting larger as we go down. But as I said, more about this in chapter 9.